Oh, oops, got them wrong. 4v. 8.
Yeah. And then you take the second one. Still checking this. I didn't like this.
See, someone can check my math. Is that what y'all are getting?
Yeah.
That's 4v minus 3u. The numbers are going to be ugly. I mean, I didn't promise you that they were going to be nice. And then magnitude. Is the square root of the sum of the squares of the components. That's right. Well, actually, it's backwards from what you think. The whole time that you've thought they're absolute values, they're actually, those bars mean a norm. And a norm is a way that we measure something. And when you're dealing with a number, it's easy because it's just the length, it's the distance from the origin to the number. So it's always spitting out, like if it's -5, it spits out 5, right? But it's a measurement of length. With numbers, it's one-dimensional measure. With vectors, it's something different. And you can have those bars on a lot of different things, like functions. You can measure the length of a function. So, yeah. Okay. What is this? Square root of 806. And that's what we would leave it as. We could get a decimal approximation, but we want to keep things exact without any rounding error. So just root 806. All right, that's straightforward. I realize for a lot of you, you've seen this, okay? And I'm sorry, there will be a point where you see something new for the first time, all right? Eventually. It'll happen sooner than you think. The only thing I would say on this, in my work, what I did was I distributed a +3 through the u, and I left a negative outside. You could distribute a -3 through and replace it with a plus in between the two vectors. Just it's up to you how you do that. You should get the same result.
So like you said, you could distribute -3 to the u?
I could go hit that with -3, it'd be 15, -21, and then 6, right? Yeah. But I should have a plus out in front now. Like this would be replaced with the plus when I'm adding them together.
Because I did that, like I put negative again, so like that messed up my.
Yeah, that would have, yeah, if you did negative twice, that would have changed it. All right, that's it. Now, unit vectors. These are going to be very important later, all right? Unit vectors. So any vector with a length of 1. So that means when you take its measurement and you get the answer of 1, it is called a unit vector. Like we just got root 806, right? That was not a unit vector. If we got 1 as an answer, it would be. Any vector with length 1 is a unit vector. So there's infinitely many unit vectors, right?
Like the unit circle, like it's 1. Like
Yes. Yep. Unit meaning 1. So would you agree that if I give you a vector, which is the blue one, right? That blue vector has a length and it has a direction. Yes? Do you agree with this statement? I can always find a unit vector pointed in the same direction. So if I give you a vector, I should be able to come up with a vector that points in the exact same direction but has a length of 1. I should be able to. I mean, I should say it should exist. Like if I move this over here, notice that that red vector is always a length of 1. Even if the vector's smaller, right? Even if the vector's shorter, I should still be able to point something out in the same direction and have a length of 1. With the exception of the 0 vector. I should not be able to find a vector pointed in the same direction as the 0 vector. So that's our one limitation. How do we do it though?
With the 0 vector, is it either pointed in all directions or is it not pointed?
We could get into a debate on that. Yeah, it's you can't really say it's pointed in all directions, but you could argue it's pointed in all directions or no directions. Yeah, yeah. We won't even talk about the direction of the 0 vector. Okay, so if we are given a vector, like I said, this is going to come up later, and I'm not going to prompt you and be like, oh, remember back in 10.2 when we were talking about this? This is you just need to remember this, okay? If somebody hands you a vector, here's how you compute a unit vector pointed in the same direction. Here's how you find that red vector that I just showed you, all right? Now let's see if it makes any sense. What you're going to do is you're going to take, where am I? Whoa, what just happened? Lost it. There we go. What you're going to do is you're going to take the vector that you're given, u, and you are going to multiply it by this. Now somebody tell me what that is.
The inverse of the magnitude?
The inverse of the magnitude? Yes, we could say inverse. That's, as long as we all understand inverse to mean what you're saying. Yes? Is that what I circled out there a number or a vector?
A constant.
It's a number, right? 1 divided by the length of the vector. The length of a vector is a number, isn't it? So 1 over the length of a vector should just be a number. So isn't this a scalar? Isn't this like a c? This is like a c sitting in front of my u. But the c that I'm choosing is actually the reciprocal of its own length. In other words, I'm dividing this vector, each component, by its own length. And what that has the effect of doing is creating the length of 1. So let's see this done as an example. Here's another way of writing the same thing. You take the vector u and you divide it by its own length. That's the same as taking 1 over the length of u and scalar multiplying it through. Yes?
Now, would you have, since it's represented like that, would you split it up? Like
Split it?
one would be like the square root of x1 plus y1 plus z1.
I'm not sure I understand. How about we do this example,
Okay.
and then we'll see if that answers your question. Fair? So here's a vector v. Find a unit vector which points in the same direction. Okay? So what do I need in order to do this? I've got to find the magnitude of this. So what's the magnitude of v? Square root of 4 plus 9 plus 25, which is the square root of what? 30. I can't do the arithmetic. 8? All right.
Yes.
Okay. 34, 8, yes. Root 38. Sorry. My brain just stopped doing arithmetic a long time ago. Yes? Now what? What do I do with that? Yeah, I'm going to take that vector and scale it by the reciprocal of this. So I'm going to take 1 over this and multiply it times the vector 2, 3, negative 5, like this. So there's my C times my V, and now distribute that through. This really just turns out to be 2 over root 38, 3 over root 38, and negative 5 over root 38. How do you know that these are pointed in the same direction? All I did was scaled it, right? I scaled it by a number. And so they're parallel, right? And it's pointed in the same direction because it's not a negative number, right? This is a positive number, so it should point in the same direction. So all I've done is shrunk or stretched out this vector. That's all I've done, right? Now, that's our answer. This is a vector that points in the same direction as that one, but has a length of 1. Can we check that that has a length of 1? Yeah, why don't we check that? What is the length of that vector? Let's try it real quick. Length. So wouldn't you just take the square root of the sum of those things squared? So check out what happens. Square that, what do you get? 4 over 38. Next one, 9 over 38. Next one, 25 over 38. They all have the same denominator. Add them together, 38 over 38. Root 1 is 1. So that is a unit vector. It works. All right, do not forget how to find unit vectors. Well, we're actually going to need that. Do you remember I was trying to motivate like the ideas of this class, and I said that in Cal 1 we found the slope of tangent lines on a curve, and that here we're going to look at a surface and we're going to try and find a tangent line? Well, when we do that, we actually need to know which direction to point in. And when we talk about what direction we point in, the formula that we're going to use requires that we convert the direction vector into a unit vector before we do the formula. And if you forget to do that, it'll be wrong. So it'll come up later. No. This right here? This? No. This? Oh, yeah, later on? Yeah, it's a tangent vector. Mm-hmm. All right, standard basis vectors. So there are, in two-dimensional space, there are two very, very important vectors, which you see in physics and engineering. It's I hat, j hat, right? And those they're just vectors, but they're special. I hat is the vector 1, 0, and j hat is the vector 0, 1. And in three-dimensional space, you have three special vectors. It's I hat, j hat, k hat. Oop, that's the next slide. I'll do that in a minute. But let's talk about why these vectors are so important, right? Why we use them. The reasons why they're so important is because, first of all, they're unit vectors. And unit vectors are easy to work with because them having a length 1, as you multiply things, having length 1 helps things stay in control. I mean, it's like when you multiply, 1 doesn't change anything. Same sort of idea. The fact that they have a length 1 is a good thing. And then every vector in two-dimensional space, every vector, can be written as some linear combination of these two vectors. All that means is this. You give me a vector. Okay, I'm going to just draw a vector here. There's my vector in black, okay? There's my u vector. What I can do is I can use vector addition, right? You know how we add vectors, tail, you know, you go tip to tail, all that? So what I do is I take I hat. I hat is the vector 1, 0, right? J hat is the vector 0, 1. So if I were to look at those, that's this, I don't know if you can see the green from where you're sitting, but that's this one, right? That's I hat, and this is j hat. So in order for me to draw this vector here, all I need to do first is take I hat and scale it. And that would scale, if I scale by 2.64, it'll draw this red vector. Then I take j hat and I scale that one by 2.65 in this case. And if I take this vector and go tail to tip like that, I will draw that result. And that works for any vector in two-dimensional space. I can always come up with some combination of I and j. Like that one there, I would have to take I, scale it to make it longer, multiply by negative to flip it over, and then j the same thing. So basically, I can create every vector in two-dimensional space from just those two. Okay? What do we call those in linear algebra? No, you remember? No. These are called basis vectors for the space. And in fact, they're more than that. It's called an orthonormal basis, meaning not only can you create every vector in this space, ortho means perpendicular. They're perpendicular to each other. And normal means they have a length of 1. Because you can actually draw every vector in two-dimensional space using any two vectors. Like if I just say I'm going to use that vector, and I'm going to call that I hat subscript r because that's Robert's I hat, and then I'm going to use this vector right here. I'm going to call that j subscript r. So for me, those are my two favorite vectors. All right? I can create any vector from these two. Because if I draw another vector here, I would just have to scale these appropriately, tail to tip, and I could get here. I could get from here to here if I scale appropriately. I probably have to make this one a little longer, take this one, add it, and then multiply by negative, point it in the other direction. Do y'all see that I could get to the blue with these two? So these would be considered basis vectors for the space, because they make up the whole space. But they're not orthogonal to each other. They're not perpendicular, and they don't have length 1. I know I'm getting a little bit beyond what we should be talking about. But if you're going to take linear algebra, or you're taking it now, or it's in the future, when we talk about basis vectors for spaces, I hat, j hat in two-dimensional space are like the best we get that you can get. They create the space, they're orthogonal, and they have a length of 1. IJK in three-dimensional space is exactly the same. Plus, I just like saying orthonormal basis. That's just something you don't get to say every day, right? They are orthonormal. They form an orthonormal basis for the space. So I hat, j hat, k hat in three-dimensional space are a little different because you have to have, in three-dimensional space, you have to have that third component, right? So it's 1, 0, 0, it's 0, 1, 0, and then 0, 0, 1. And guess what? Those just point out the x-axis, the y-axis, and the z-axis. Just out 1, up 1, over 1. And you can create all vectors from those. Now, I am not a fan, just personally, I just don't use I hat, j hat, k hat that much. I don't like to use it. I think mathematicians are less like into the I hat, j hat, k hat thing as engineering and physics. So please understand that in this class, when you're not seeing it a lot, it's just by choice. And here's why. How would you write that vector using the standard basis vectors? So I have a vector 2, 3, negative 5. If I want to write that using the standard basis vectors, here's what I would do. I could look at that as being, let me just see if you agree with this. See if you agree with that. Negative 5. Sorry, I'm off the board here. Do you all agree that if I add these three vectors together, I get that? Yes. Okay, and then do you agree that if I pull out a 2 out of that first vector, scalar multiplication, I pull out a 3 out of the second vector? Yep, and if I pull out a negative 5 out of this last one, right? That's true? And then this is I hat, j hat, k hat. So this is 2 I hat plus 3 j hat. Do y'all hear, do they say something other than j hat? Do they say ijk? Okay.
I've also seen it as like E sub 1, E sub 2.
Okay, E sub 1. Yep. That's more linear algebra-ish to have E. I like that more. Subscripting to me is always better because when you start using letters to represent something like this, like these are the standard basis vectors for three-dimensional space. What about four-dimensional space? Maybe you have I, J, K, L hat maybe. But what about like 100-dimensional space? What's your basis vectors look like? I, J, K, you're going to run out of letters, right? So you go to subscripting instead and you don't worry about it. All right. So does everyone understand that this written with angled brackets is equivalent to that written like that? The big difference is that you have addition and subtraction between these. So this is like one string of things as opposed to things that are separated by commas in angled brackets.
Yeah, do those need to be in brackets?
No.
That's one vector adding to another vector.
That's right. This does not, in fact, it should not be in, this should not be in angle brackets. Because then what it would be, huh?
Not angle brackets, because I've seen them in like little brackets, like squiggly brackets. Like,
I know what you're saying. Like this?
yeah, like that.
Yeah, we get some notation things here. I've seen this used for vectors instead of this. So I've also seen vectors written vertically instead of horizontally. So, I mean, it's true. You can write
I'm
this.
just asking, how do you want to see it?
You can write this vector this way also. This is more linear algebra. You can do it that way. But I'm going to stick with, this is what I'm going to use most of the time. I just think this is the easiest to work with, personally. The book will sometimes present you with something like this, and I expect that you're going to be able to make the connection. All right. How are we doing on time? 20 minutes. Not good. Are we ever going to get... Okay, we're done with this. All right, that is it for that section. And I've been looking everywhere to try and find my homework list. I have a list that has all the homework problems, and I cannot find it. So I'm going to just continue to send you the homework until I find it. All right, we're going to start 10-3. We still have 22 minutes. Here's what we've defined so far.
Isn't this like the projection of one vector to another?
Well, yeah, we're going to have to find out. If I said that you learn numbers, you learn how to multiply two numbers together, it made sense, right? Give me a number, give me a number. I multiply them, right? You get a dog and another dog, put them together, you get a dog, right? I mean, like, that's what happens, right? That's normally that's what's happened in our life. So here what we did is we put together a number with a vector and it spit out a vector. It spit out a vector, right? This spit out a vector. It may have stretched it or shrunk it or changed the direction or something like that. But number, vector, gave us vector. What we are looking at now is is there even something out there that allows us to do vector times vector? And the question is this even possible? And what the hell does it mean? What do you get out? Do you get another vector, right? Well, it turns out that in mathematics, when it comes to vector times vector, we have two standard definitions for vector times vector. Now, this is not the same in math the way you've learned it, right? When I say 4 times 8, you don't ask me which times are you talking about, right? We all understand 4 times 8 is, what, 30 or something like that, right? So if we say vector times vector, you actually have to ask me, what multiplication are you talking about? Because there's two of them. There's the dot product and there's the cross product. There's two of them. And the first thing we're going to learn is the dot product, and then we'll learn the cross product. Understand? Okay, so this is, can we do this? You know, can we? Yes. But there are two types. There's dot product and there's cross product. And there's others, but these are the ones that you can use. These are the ones that are most applicable to what we do. All right, dot product. Let's start with that one. For the dot product, it turns out that when we put the dog and the dog together, we're going to get a cat. Okay, it's vector times vector equals number. All right, that's what's going to happen when we do a dot product. Now, this is a lot of gibberish up here, which is why I provide these online. So the dot product, also called the scalar product, also called the inner product. Different language, depends on what level of math class you're in. When you get pretty high up there, we call these inner products, but it's called the dot product here. If you're like a math major, then the dot product is a certain type of inner product. Inner products are more general. So the dot product is given two vectors in R2. So we'll start with two-dimensional space. Somebody hands you two vectors, v1, v2, u1, u2. And you want to do the dot product, you will write u dot v, and this dot is like a kind of a bolded dot. And in the book, you'll be able to tell the dot, it's bolded. That lets you know it's a dot product. And all you're going to do is take the components v1 and u1, multiply them, and then add them to v2, u2 multiplied. So you're going to multiply the components and add them. And this should result in a number, right? Because you're doing number times number plus number times number. That gives you a number. And I say that here. So the dot product is the sum of the products of the components.
What does that look like in like?
I knew you'd ask, and I'm going to answer that. Question is, what is it like? What does it mean? Like, what is that? What does that number actually mean? Right? Okay. All right. It's vital to understand that the result of the dot product is a number, and the answer is not a vector, and that we use the bold for the dot. In three-dimensional space, if you have a vector in 3D, you've got three components: v1, v2, v3, u1, u2, u3, and it's the same exact thing. You take the x components, multiply them, the y components, multiply them, the z components, multiply them, add them all up, you've got a number, yay, you're done. Dot products are very clean, very simple to compute. Again, the answer is a number. I guess we can take 15 seconds to do this. What's u dot v here? So you're going to do 2 times -3, right, plus -3 times 4 plus 5 times 7, right? That's what you're doing? Just multiplying all the components together and adding them up. What do you get?
You get -6,
53?
6, 12, 18 plus 35. Yeah, 17.
17? We'll go with what most people are agreeing with. 17?
I'm nothing. Yeah, -6,
Okay.
-12 plus 35.
All right, so we got 17. So we took these two vectors that live in three-dimensional space, we dot product them, and it spit out 17. And we're like, well, so what, right? What does that mean? Who cares, right? Like, what is the value, right, Eric? Like, that's what you're asking, like, who cares? Like, what's 17 represent? All right, so I'm going to try to answer that. But before I can answer it, I have to just give you a couple of properties of the dot product, some cool results. First of all, if you take a vector and you dot it with itself, then you're going to take the u1, right, because it's the same number, and then you add to it u2, u2, and then u3, u3, and that actually would kind of look familiar. That's almost the magnitude. That's almost the magnitude. But we didn't square root it. So it actually turns out to be the length of the vector squared. So if you dot a vector with itself, you get its length squared. It's kind of interesting. The dot product, the dot product is commutative, meaning u dot v is the same as v dot u. And that's just because multiplication is commutative. The dot product is distributive over addition. So if you have u and you want to dot it with v plus w. Now, v plus w is a what?
Vector.
Is a vector, right? Two vectors added together is a vector. So if I take u dot with this vector, I should get a new vector. This property says that you can really distribute the dot product through. So you could dot u and v first, then dot u and w, and then add those two vectors together. Or sorry, those two numbers together. Scalar multiplication can move through the dot product. So if you have a scalar sitting in front of something and you're dotting, you're free to move that scalar anywhere you want. You can pull it out completely, push it to the other vector, the scalar slides around. We're not going to prove all these properties. You just have to, you could go mess with it yourself and prove it to yourself. And then the last one, if you take 0 and you dot it with v, the 0 vector, and dot it with v, you get the number 0. Make sense? All right. So that's the mechanical part of it. No, we're not doing that. The dot product theorem. This is now we're going to answer the question, why is the dot product useful? What is the point? Well, it's not easy to show. Well, it's not that it's hard to show, but we actually don't have a lot of time to show this. I believe the book goes through the proof of this, and it uses, I forget what they use to show it, but I'll look in the book later, and I'll talk about it next class. This is a theorem. So in mathematics, theorems are things that are, basically a mathematician comes along and says, hey, I think this is true. Like some mathematician came along and said, hey, I think that the dot product of two vectors is actually equal to the length of the first vector times the length of the second vector times cosine of the angle between them. And then they went and proved with mathematical rigor, some sort of proof, they proved that this is true. So anytime you see a theorem, it's something that was proven. So it has been proven, I'm not going to prove to you, that the dot product, that number, is just the lengths of the two vectors multiplied together times cosine of the angle theta between them. So imagine we have two vectors. Okay, they don't have to be the same length. Here's a vector pointed in that direction, here's a vector in this direction. If I take the length of this vector and the length of this vector, multiply those two numbers together, and then multiply by cosine of the angle between them, that number, what's that? What's the angle between them? I was hoping you would ask that. Because I'm about to move them, right? So I'm going to move them right here. Okay, there they are. See that? Yes? Now I'm going to rotate it just so everyone can see it. See that triangle like that? I'm talking about that angle. This one right in here. Understand? It doesn't matter. You tell me where to put them. It doesn't matter. I can put them, like that. If I put them together, slide this one here, then I could rotate. Oh, sorry, I hit the wall there. I could rotate them in a way that you could see that angle, right?
So to get theta, would you use the same process? Just,
Yeah, the question is being asked. This means we might be able to actually find the angle, right, between two vectors, and that's coming. Yes, that is coming. But before we get to how we can use this to find the angle between two vectors, let's look at a very, very nice couple of results, probably the most important result from this theorem. Everyone got this formula? U dot v is equal to length of u times length of v cosine theta. I want us to talk about a few things. First, if somebody gives you two vectors, why must the angle between them be between 0 and pi? Let me get my vectors back out here. Pi is how much? Pi is 180? Okay, so here's two vectors, right? Obviously the angle between them is between 0 and 180. So what if I go like this and I open it up and now I go past 180? Why don't you have to worry about that? Now I can look at this angle, and this is the angle between them. Understand? So even though this opened up more than 180, now I go to the other side and look at this angle. That's the angle. It's going to be smaller than 180. Or the worst it could be is that they're pointed in opposite directions completely, right? Then they're parallel, right? If the angle between them is 180, pointed that way and this way, cosine of 180, -1. Okay, so things are going to start to come together here. Yes? All right, so we all agree with this first, yes? All right, now consider the cosine function, what we learned in pre-cal. What if your angle is 0? What can you tell me about cosine? Cosine of 0 is 1. So here if I have two vectors and the angle between them is 0, that means that they are pointed in the same direction, right? And that means that the dot product is just going to give us what? The dot product will be the magnitude of u times the magnitude of v times cosine of 0, but cosine of 0 is 1, right? So it's just their lengths multiply together. So if I've got two vectors pointed in the same direction, and I say, give me the dot product, all you're going to be doing is taking the length of this one times the length of that one. That's what that number will represent. That's not very useful, but it's good to know.
So with that, since you're multiplying the lengths together and one of them's not scalar, it's not like you're scaling the vector
That's right.
to a certain amount. So
It's kind of, this right here is not that useful. Okay, this is not that useful. What's about to come, I've got it highlighted in here, is the most useful part. That's what happens if the angle is 0. Yes?
So if the angle's at 90?
Yep.
Okay.
Yep, exactly. I think you're seeing it. What happens if the angle is pi over 2? 90 degrees. Cosine of pi over 2 is 0. And that means that if your vectors are perpendicular to each other, right, then the dot product should spit out what number? 0, right? According to this formula. U dot v should be the length of u times the length of v. Now these are not 0, but cosine of pi over 2 is. And so regardless of these, you get 0, don't you?
Yes.
And that actually gives us a theorem, which I've got highlighted right here. U and v, two vectors. This is the main result, okay? Two vectors, u and v, are perpendicular to each other, or orthogonal is the other word we use to describe perpendicular. Two vectors are orthogonal if and only if their dot product is 0. Now, do you all know what if and only if means?
Yeah. It's a logic statement.
It's a logical statement, but logical, I didn't quite catch the end of what you said.
Yeah, it's like a necessary and sufficient condition.
Yes, okay, so what we have to understand is what are called forward and backward implications. So I'll try and explain it in a very simple way. This is my famous example. It's not famous because people like it. It's the one I always use, okay? Let's say that you live in Texas. If you're from Texas, then you live in the United States of America, right? Let's not get into illegal and all that. Let's just say if you live in Texas, you're in the United States, right? Geographically. That's true?
Yes.
Okay, at least now, unless Texas decides to bail. If you're in the US, then are you in Texas? No, not necessarily, right? You could be, but you don't have to be. So the implication of this statement this way is true, but the implication the other way is not true, right? Whenever you have a statement that the implication works both ways, then you can use this if and only if. And that means that's super important with this theorem, because it means that if you've got two vectors that are orthogonal, then the dot product must be 0. But it works the other way. If your dot product is 0, they must be perpendicular. Okay? Very important that it works both ways. So that right there gives us basically a way of checking for orthogonality between vectors. That's a super quick check because you can compute a dot product, right? I mean, I think it was pretty easy to compute that. And if you get 0, guess what? Your vectors are perpendicular. Amazing.
And if you get a negative number, that means that they are opposite, like in opposite directions? Or?
Yeah, I've got a picture here, an animation that kind of helps explain like the different scenarios. So I've got two vectors here. All right, I've got two vectors. I've got this one here, and I've got this one here. This is measuring the angle between them. And I have the computer computing the dot product for us. All right? So right now I'm getting a negative dot product. And let's just see how things change. Just keep an eye on your dot product. It's still negative, right? Dot product is about to go to what here? 0, because I'm about to be perpendicular. And then once I get over here, my dot product is positive, right? Come down here, dot product should be, this number right here should be the length of the first one times the length of the second one. So the length of this one's 1, the length of this one's 2, multiply those, we're getting about 2, right? What happens if I drag this one down? Is it going to be positive still, negative? What do you think? Positive. Still positive, because the angle between them is acute. It's so cute, isn't it? And then we go over here, and we get negative dot product once we're here. So really what you can say is, if you got a negative dot product, you have an obtuse angle.
So it doesn't matter which side of the y-axis.
It does not matter. It's the angle between them. If the dot product is positive, you have an acute angle. If the dot product is 0, you're perpendicular. And really, there's not an easy way to check if two vectors are parallel. Oh, wait, yes, they are, because they just have to be scalar multiples, right? So like we have, and there turns out to be another way that's coming up later to check for parallel without checking the scalar multiple.
Determine the angle between vectors, and we're shifting vectors, it always has to be tailored into Theorem, not tailored.
Nope. Yeah, it's amazing. This is an amazing thing. All right, we're not going to have time for that. Next class, we'll talk about the angle between them and how we can find it. So if you give me two vectors, how do I find that angle? Yeah, I don't even think this problem is really even worth. Well, I mean, I've got a minute. Y'all can start packing up. They want me to, or I want you to compute u dot v here, and I give you the magnitude of u, magnitude of v, and I give you the angle between them. So all you have to do here is what? Magnitude of u, magnitude of v, that's not v, and then cosine of 31 degrees. You just need to make sure on your calculator you're in radians, degrees, sorry. So this would be 3 times 7 times cosine of 31 degrees, and you'd get some number here, and blah, blah, you're done. Okay, we will pick up next class with finishing this off. We do not have class on Monday. I have it on the schedule that we do. That was just, I was hoping y'all would not want to have the holiday and we just all come in here and do more. No? Sure. Okay, so Monday's a holiday. I will see you on Wednesday. And I think I'm going to hand you your first take-home exam on Wednesday. I'm going to give that to y'all. So do your homework. Yes? I've not done the sign-in sheet. Y'all go. It's too late. I've forgotten already. Y'all need to remind me beginning of class or something. That's 2 days in a row. Yeah, let me turn off my camera so.
So are you still going to give us extra credit for your cussing habit?
Extra credit cussing. I haven't cussed.